Okay, this is going to be an interesting video, and because we're going to do something amazing, we'll prove this fact in 2 lines. We will also try to find Fibonacci number using matrix multiplication. Hope you will stick with me. If you feel boring, you can skip a bit apart, but try to watch the entire video. Okay, first of all, we will get sense of what we are trying to prove. What I'm trying to do is we will be trying to find Fibonacci number using matrix multiplication. Let me reveal our hero right now. What we will be trying to show is we'll show that 1 1 1 0, this matrix, when multiplied n times, we will get the following matrix: Fibonacci number of n plus 1, Fibonacci number, and Fibonacci number, and Fibonacci number, and then n minus 1 Fibonacci number. We will try to solve this. Now, if you want to convince this to yourself, you can just try for n is equals to 2. Now we know that first Fibonacci number is 1, second Fibonacci number is 1, third Fibonacci number is 2, fourth Fibonacci number is 3, and zeroth Fibonacci number is 0. Yeah. If you want to convince yourself, for n to the power 0 power, this does satisfy, right? For 0 power, this is just 1, right? So does it satisfy? Yeah. For 0 power, how is it supposed to satisfy? For 0 power, it's not defined actually, because n minus 1 is f of minus 1, which is not defined. So this is only for n belongs to positive integer. Okay, now for 1 power, we have 1 1 1 0, right? And this is f of 2, f of 1, f of 1, f of 0. So f of 2 is 1, f of 1 is 1, f of 1 is 1, and f of 0 is 0. So that works. Now let's check for n equals to 2. 1 1 1. We will also prove this. We are just getting intuition right now. We will prove this formally later on. If you want to multiply twice, I know how to multiply, right? 1 into 1 is 1 into 1, 2, and then 1 1 1 0, 1 1 0 1 1, 1 1 0 1 0 1. So this is our because n is 2, this is supposed to be f of 3, right? Yes, it is f of 3. And these two are supposed to be our f of 2's, yes, and this is supposed to be our f of 1, right? Let's say if we take its cube, in the cube, when the n is 3, again this will be multiplied by 1 1 1 0, right? So 2 1 and 1 1 3, 2 1 and 1 0 2, 1 1 and 1 1 2, 1 1 and 1 0 1. And now this is our f of 3, these two are f of 2's, and this is our 1th Fibonacci number, right? So you see that this does hold true. You can say it like this. Or if you want to prove this statement, you can also prove by induction. In induction, what you can do is, first of all, you can verify for n is equals to 1, which you already did, right? Now assume it's true for k. That means you can assume that 1 1 1 0 to the power k will just be this thing, f of k plus 1, f of k, f of k, f of k minus 1. And now try to prove for k plus 1. K plus 1, we should get the following result. To the power k plus 1, we should get this to be f of k plus 2, f of k plus 1, f of k plus 1, f of k, right? And let's see if you can get that or not from the LHS. We can break LHS into 1 1 1 0 to the power k, right? Or let's say 1 and 1 0, and then 1 1 1 0 to the power k. Now this is 1 1 1 0, and we have assumed this thing to be f of k plus 1, f of k, f of k, f of k minus 1, right? Now if we multiply this, we get 1 1, and this thing will be f of k plus 2, 1 1, and this 2 will be f of k plus 1, because f of k plus f of k minus 1 will just be f of k plus 1. This 2 will just be f of k plus 1, and this will just be f of k. And so we have proved this, and this is how induction proves that this will indeed give this thing. But we will try to prove this using matrix multiplication. Yeah, and the reason is, if we use matrix multiplication, we will not really get Fibonacci number. We will get a formula in terms of power n and other numbers. And since we know that those are the Fibonacci numbers, so we will basically get an expression for nth Fibonacci number, and that will be helpful to find any Fibonacci number for any n, right? So yeah, now I will give the proof right now because I've already exposed this. Since we know that this holds true, since we know that though we don't have an explicit expression for nth Fibonacci number right now, we need to do matrix multiplication for that, though we don't have explicit expression for this right now, but we can still prove this theorem using this relation that we have derived. Right, so how we can prove this is f of n plus 1, f of n, f of n, f of n minus 1. We know that this is equals to 1 1 1 0 to the power n, right? Now if we take determinant in both sides, what will we get? We know also, I think you know that determinant of AB is equals to determinant of A, determinant of B, right? We will be using this property. Over here, if you take determinant in both sides, here like over here, if I take B as A, we see that determinant of A square is just determinant of A square, right? Similarly, if there were n A's, determinant of n A's will be equal to determinant of A n times, so determinant of A to the power n, right? We will use this thing. So over here, this will just be f of n plus 1, f of n minus 1 minus f of n square. Over here, this will be determinant of 1 1 1 0 to the power n, and we know that this is just 1 into 0 0 minus 1 into 1 1 to the power n. So we see that this can be easily proved. F of n plus 1, f of n minus 1 minus f of n square is equals to minus 1 to the power n, right? If you want to convince yourself that this formula is true, though we have already proved, we can also check this with some numbers. We have here some numbers. Let's also, I know a few. F of 3 is 2, f of 4 is 3, f of 5 is 5, f of 6 is 8, f of 7 is 13, f of 8 is 21, right? Now let's say if I take n is equals to 5, then f of 6 is 8 times f of 4 is 3 minus f of 5 is 5. This should be equals to minus 1 to the power 5, right? So 24 minus 25 is equals to minus 1, minus 1 is equals to minus 1. See, this is true. Now let's say if you have n is equals to 6, then we should have f of 7, f of 5 minus f of 6 square is equals to minus 1 to the power 6, right? F of 7 is 13, f of 5 is 5, minus 80 square is, this is 1. 13 into 5 is 65, minus 64 is equals to 1, 1 is equals to 1. See, that's true. And this is an amazing theorem and amazingly proved using the matrix expression, right? Now, finally, it's time to find the exact product of this 1 1 1 0 multiplied n times and an explicit formula for f of n. Now, here begins our amazing journey. Now, for that, what we will basically try to do is, first of all, we will try to find a way through which we can multiply a matrix n times. Let's say, what if I want to multiply this matrix 100 times? How do I do that? We want to find such a way, right? Again, for that, to find that way, first of all, for some unknown reasons that you don't know, that you might not know right now, it's also important to know about some eigenvectors, eigenvalues, and yeah, I think those things. Now let's say if you want to exponentiate a matrix. First of all, we want to find we want to find two vectors there, which when multiplied to this matrix just get scaled out. I think it's better if I just go with the process and I will explain in the middle. So let me just go with the process for now. We know that we want to exponentiate this matrix to the power n, right? First of all, I will find its eigenvectors and eigenvalues. I will explain in the middle that why these things make sense. Now let's say there's a vector b for which this matrix just get scaled out, like nothing else happens. There will basically be two such vectors if this matrix spans an entire plane. Okay, yeah. Let's say exists such vectors for which this matrix just scales this vector. So since it just scales it, I can write it as lambda. I can take it to other side. B vector minus lambda B vector is equals to 0. Now I can introduce an I over here, because lambda times I matrix will just be same, because the reason is I want to take vector b common. So 1 1 1 0 minus, this will be lambda 0 0 lambda is equals to 0. Now if I take determinant in both sides, you know that vector b will basically not have a non-zero determinant. So this is the thing that will have zero determinant of 1 minus lambda. But it's not really not the way that you understand. The way you understand is basically through how, for to become a zero vector, determinant has to be a 0, because it has the dimension has to scale down to become 0. So that's why to put the dimension to scale down again, the determinant has to be 0. So that's how you understand. But I feel like I'm overcomplicating stops. Understand however you want to. Now 1 minus lambda, this should be equals to 0, right? Now we will have 1 minus lambda times minus lambda minus 1 is equals to 0. This will be minus lambda plus lambda square minus 1 is equals to 0. So we will get two values for lambda. Lambda is equals to minus p plus minus square root of b square minus 4ac by 2a. So let's say we get lambda 1 as 1 plus root 5 by 2, this is the bigger value, and lambda 2 as 1 minus root 5 by 2, which is the smaller value, right? Now these are some special values. These are some not just random numbers. These are actually the golden numbers, golden ratios. Let's note this by phi 1 and phi 2. And there's a special property of this, that phi 1 times phi 2, that will just be, what will it be? 1 minus 5 by 4, which is minus 1, right? The product of these two numbers will just be minus 1, and if we subtract one from the other, let's say if I subtract phi 1 minus phi 2, I will just get root 5, right? Yeah, these are just some like properties of these numbers which will be helpful later on. Now, yeah, these are special numbers. Now we know that these are its eigenvalues, and we also need to find out for which eigenvectors are these the eigenvalues. Let's try to find that. Now for that, we just noticed that okay, so we just noticed that these are eigenvectors, right? Let's say I'll just write phi 1 for now, and I will try to find eigenvectors for phi 1, and the same process can be used for phi 2. So I will not basically be doing for phi 2. Now if I take it to other side, what we will have is basically 1 minus phi 1, 1 minus phi 1, 1 1 minus phi 1, right? If I take it to other side and then take b vector common, I think you understand that. Yeah, let B vector be AB. Are you understanding it? Basically, I took it to other side and then took B vector common. This is our B vector for now. AB. This is our B vector. And since it was to be an identity matrix, phi 1, 0, 0, phi 1 and subtracted. So that's why we got this expression. Now if I multiply this, I will get 1 minus pi 1 times A plus B is equals to 0. Similarly, A minus B phi 1 is equals to 0. Now over here, you might notice that AB can be 0, 0, which is a trial solution, but we aren't looking for that. We are looking for some real vectors, because we do know that 0, 0 vector will just get scaled by a constant, but we are not interested in that. We are interested in some other vectors. So you might notice that over here, what you can do is, if you say A as phi 1 square and B as phi 1, this will become 0, right? Similarly over here, that will also be 0. So these will be solutions. Over here, we will get phi 1 square minus phi 1 cube plus phi 1, right? Now after that, how do I deal with phi 1 cube? Okay, wait, let me see. How do I deal with phi 1 cube? Over here, we have this property that for phi lambda square is lambda plus 1. So maybe what I can do is, I can write this as phi 1 times lambda square lambda plus 1. So phi 1 plus 1 plus phi 1. So this is phi 1 square minus phi 1 square minus phi 1 plus phi 1. So this is 0. You see that, right? See that, right? I just use this property that lambda square is lambda plus 1 for phi. So basically, if we substitute these A and B values in the first equation, we got this expression, and this expression reduced to 0. So that means these two values satisfy both equations, right? So for the corresponding eigenvector or eigenvalue of phi 1, our eigenvector is phi 1 square times phi 1, right? Good. Now for the next one, also maybe I can reduce this as phi 1 square to phi plus 1, right? This is also same as phi 1 square is phi plus 1, so phi plus 1 plus phi 1, whatever, that's same. Now for the next case, if I take eigenvector as phi 2, eigenvalue as phi 2, the eigenvector that I will get is basically phi 2 square phi 2, or also you can say it as phi 2 plus 1 or phi 2. Now the magic with the eigenvalues and eigenvectors is that this can be used in a really clever way. Now what I can do is, now I know that if I multiply 1 1 1 0 with these two vectors, I will just get a scalar multiplication of them, right? Let's say if I multiply this with these vectors, phi 1 square phi 1 and phi 2 square phi 2, what I will just get is these things. Now I don't know if you know this or not. So but basically, if you are multiplying any matrix by A, B, C, D, over here in the first column, what I will get is just the product of this matrix with vector AB, right? Over here I will just get product with vector AB, and in the second one I will just get product of CD with this matrix, right? So what happens is, this is same as in the first column, we will just get product of this matrix with this vector, and we know that this vector is just scaled, right? And for the first vector, the eigenvalue, that scaling value was lambda 1, so this will just become lambda 1 cube and lambda 1 square, right? And this will just become, now for this vector also, this has just scaled by a value, and its value was lambda 2, right? So this will become lambda 2 cube. It's not lambda, it's phi 2 cube by phi 2 square, because this will just get scaled while multiplying with this matrix. That was how these values are found, right? Now we know that like these are just scaled, right? This phi 2 was scaled by phi 1 square is scaled by phi 1, phi 1 was scaled by phi 1. Again here also phi 2 square by scaled was scaled by phi 2, and over here this phi 2 was scaled by phi 2. Now we can write this in an amazing way. How we can write this is same as like phi 1 square, phi 1, phi 2 square, phi 2 being multiplied by phi 1 0 0 phi 2. Now the what happens is this number, if I write a and then 0 over here, what this does is this a will just be a scalar multiple for this first vector. This a over here will just scale the first vectors in here. So that's what it's being done, right? So if you ask me why, if you ask me, you can just see it by multiplication as well. If you just multiply, first of all, this to multiply, so this will just multiply this one, 0 times this doesn't matter. Again, if you multiply, this will scale this one. You can just see it from algebra. But if you also want some perspective, what happens is, you can, if you see it through transformation, first of all, this is an this is what to say, this is a set of coordinates with x, with let's say the I vector being phi 1 and z 0, and when we scale by this value, this there is just this x thing, so it will just scale this one, something like that. But yeah, I'm not good at explaining, but yeah, you get the idea, right? Because you can see it from the simple algebra itself. Now after you are able to make this conclusion, after you are able to understand up to this step, now what we will do is, we have got some amazing result. You see, we have got that 1110 times phi 1 square, phi 2 square, phi 1, phi 2, this is equal to phi 1 square, phi 1, phi 2 square, phi 2 times phi 1 0 0 phi 2, right? Now what we can do is, I think you know that, let's say if I have a b c d, if I just multiply to the left end, or sorry, the right end of both, so I can multiply by the same thing to the same end of both product, right? I can multiply here by b inverse, also here by b inverse. I can introduce b inverse here because I have to introduce it to the same side. Yeah, if I introduce it to the same side, I can do that. Now this will just be I, right? So this will be a times c d b inverse. You can generalize this as the last thing will go to the last of the other side being an inverse. This is true in matrix multiplication. So we can do that. We can take it to other side as an inverse. So 1 1 1 0. And also notice that these two matrices are same, right? These two matrices, this is just matrix of eigenvalues, and this is matrix of eigenvectors. Again, this is just matrix of eigenvectors, and this is original matrix. So that's an important thing over here. Now this is phi 1 square, phi 2 square, phi 1, phi 2 multiplied by phi 1 0 0 phi 2 times phi 1 square, phi 2 square, phi 1, phi 2 inverse, right? Okay, now this is a surprising result, because now after this, if we see that this is some matrix M, and this is matrix of eigenvectors which is represented by P, and this is a matrix of eigenvalues, since this is diagonal, we represent this by D, and this is its inverse, we represent by P inverse, right? Now if I want to take square of this matrix, this will just be PDP inverse times PDP inverse, right? And using associativity, we can merge these two, we can write them together, right? and we know that they will become I. So this will just become P d square P inverse. You see that? M square. If I find M cube, similarly this will be P d cube P inverse, right? M for P d to the power 4 P inverse. Yeah. Now what's the big thing? Originally there was fourth power in M. Now there is fourth power in D. You might think like that, right? But since this is a diagonal matrix, it's really easy to take power of diagonal matrix. The power of nth power will just be a to the power n 0 0 b to the power n. See, so it's easy. So we have like reduced this difficult problem into a really simpler one, because it's really easy to take power of this one, right? Now if you want to convince yourself, let's say if I want to take its second power, if you want to take its second power, what happens during multiplication is a0 a square a0 0b 0 b0 a0 sorry 0b a0 0 0b 0b b square. See, so this is how it goes on. If you take it again the same thing happens. Basically a square 0 a0 a cube a square 0 0 b 0 0 b square a0 0 0 b square 0 b b cube, right? So this is how this just gets exponentiated. So this is how it's helpful. Now it will be helpful to take nth power. I hope you got the idea, and this is basically the exponentiating idea for any matrix. This can be basically used for any matrix, not just this one. And the idea is, now for this one I just did without any such like formally stops. I just went and using intuition and logic only. But yeah, if you know that this should be the matrix of eigenvectors, this should be the matrix of eigenvalues, this should be the inverse of eigenvectors matrix. So that is how we can express a matrix in this form. This is called diagonalization, where we diagonalize a matrix, right? So yeah, this is the formal things. Now let's get back to what we are doing. Now let's get back to what we are doing. Okay, now we are here. We're here. Now we want to find nth power of this matrix, right? And why do we want to find that? Because we know that its nth power will be equal to f of n plus 1, fn f of n minus 1. And we will basically be interested in the element that is over here in the diagonal, in this non-primary diagonal, right? Because that's actually the fn. Okay, so let's try to find out. We know that what will happen is just that 1 square phi 2 square phi 1 phi 2. We know that the only thing will happen is this will have nth power, and that's easy to compute, right? Right? Now to find its inverse, this will be, we know that to find the inverse of a, b, c, d, this will just be 1 by AD minus BC, and then minus D minus A. Wait, this is it? Wait, I don't know. Okay, first of all, what do we, the formal thing is, first of all, we need to find its minor and then take the transpose of minor, right? First of all, its minor is D, right? Its minor will be, since it's here, its minor will be minus C. Also, its minor will be minus B. Its minor will be A. Now its transpose A, D. Sorry, no, this is not change. D, A, minus B, minus C. Yeah, okay, fine. Okay, so what happens is basically these two interchange, and this will be minus B minus C, right? Now let's do that. I'm sorry for being silly over these things. Yeah. Now this is just 1 by phi 1 square phi 2 minus phi 1 phi 2 square, and then this will interchange. There will be phi 2 over here, phi 1 square over here, and this will be minus phi 2 square minus phi 1, right? We can take this constant in front. Now this constant is somehow special because we earlier proved that phi1 phi2 is minus 1, right? So that's why over here this constant will just be phi1 phi2 will be minus 1 times phi1 minus again minus 1 times phi2. So this is phi2 minus phi1. Now we assume that phi1 is the greater one, right, in the beginning. Yeah, phi1 was supposed to be this one, right? Okay. So phi1 is 1 plus root 5 by 2. Phi2 is 1 minus root 5 by 2. So the difference will be 1 minus root 5 by 2. 1 minus root 5 by 2 minus 1 plus root 5 by 2. That's just minus 2 root 5 by 2, which is minus root 5, right? Okay, good. Minus root 5. So we will have minus 1 by root 5, and then these things. Phi1 is square phi1, phi2 is square phi2. And now let's multiply these two matrices. Phi 1 to the power n0, phi2. Phi1 to the power n, phi2. Phi1 to the power n0, yeah. Minus phi1 to the power minus phi1 to the power n, phi2 square. This will be minus phi1, phi2 to the power n. This will be phi1 square, phi2 to the power n. Good. Now let's multiply those other two again. Minus 1 by root 5. Okay. Phi1 to the power n plus 2, phi2 cube. Right? If you multiply these two, that's so complicated here. Phi1 to the power n plus 2, phi1 to the power n. Wait, what am I doing? Okay. Phi1 square times this thing. That is phi1 to the power n plus 2 times phi2, right? Now this one minus phi1, phi2 to the power n plus 2, right? Okay. Now this one and this one. Minus phi1 to the power n plus 2, phi2 square, and this one plus phi1 square, phi2 to the power n plus 2. Now this thing. This is the only boring step in matrix exponentiation here. Now phi1 to the power n plus 1, phi2 minus phi1. But again, we have simplified a lot, so I think this much is tolerable, right? Minus phi1 n plus 1. We cannot expect everything to be too easy, right? Minus phi1 to the power n plus 1, phi2 square, and then plus phi1 square, phi2 to the power n plus 1, right? Okay, looks good. Now minus 1 by root 5. Okay, we know that phi1 phi2 is 1 plus root 5 by 2, 1 minus root 5 by 2. So 1 minus 4 by 4, which is minus 4 by 4, which is minus 1, right? So over here, phi1 phi2 is minus 1, phi1 phi2 is minus 1, right? So the minus 1 will basically change the signs. So this will be phi2 to the power n plus 1 minus phi1 to the power n plus 1, right? Over here, minus 1, minus 1. So this will also be phi2 to the power n minus phi1 to the power n. Over here, there are squares. So phi1 phi2 square will be plus 1, right? So this will just be phi2 to the power n minus phi1 to the power n, right? For this one, there are squares. So this is phi. Now, since there are, I have to take 2's from here to simplify it, right? So this will change to n minus 1. I think you get that, right? And I think this is phi2 to the power n minus 1 minus phi 1 to the power n minus 1. If I use this minus sign and also multiply with the constant, this will basically be phi 1 to the power n plus 1 minus phi 2 to the power n plus 1 by root 5. This is phi 1 to the power n minus phi 2 to the power n by root 5. This is phi 1 to the power n minus phi 2 to the power n by root 5. And this is phi 1 to the power n minus 1 minus phi 2 to the power n minus 1 by root 5. I'm really a lot satisfied with the results. Haha. Now, we know that this is just f of n plus 1, fn, fn, f of n minus 1, right? This was confirmed by the induction. So, we have the formula that nth Fibonacci number is phi 1 to the power n minus phi 2 to the power n by root 5, where phi 1 is the 1 plus root 5 by 2, phi 2 is 1 minus root 5 by 2, right? Now, it's the time to check if it really works or not, because it seems like how will such things with roots over here, such as irrational numbers, will give a perfect integer, right? Now, we can check it with the fourth power, because fourth power is not that hard, I guess. Let's check for the fourth power. Let's try to find f of 4 with this formula. Again, I know that we can use calculator. You can use that, but let me do it in algebraic way. You can also convince yourself by finding all the powers that you know using this formula. Let me do it. Now I will have 1 by 16 root 5 over here, right? And then 1 plus, we know that 41 is just 4, and that's 5, 4 times 5, right? And again plus 4c2 is 6, and then 5 to the power 3 by 2 will be there, and then 4c3 is again 4, there will be 25. Wait, first power, second, this is supposed to be first power. Sorry, in the first power there will be root, in the second power there will be nothing. Now in third power there is supposed to be third power, and then in the last one there will be fourth power, which is 25. This will be from the first one, right? Minus from second one, so it will be same, just sign interchange. Minus 4 root 5 plus 6 times 5. This is supposed to be, this will just be 5. I know, I do know that you know why this that is so. This is easy thing. Plus 25. Okay, fine. Now this is, wait, are all the roots cancelled? Oh no. So basically the sign will be opposite. This is minus plus, I'm sorry, because there's a minus thing. Oh, I don't need to do it because over here it's minus, that incorporates it. Okay, fine. 1 by 16 root 5, right? And then basically a minus will cancel out, so 8 root 5 plus, and now this is this was 8 root 5, right? Oh wow, it's, wait, am I getting just one? Or is it this 32 again? This is 32. Am I getting a true result? Am I getting correct result? Okay. Oh wait, this is, oh wait, there's an 5 up, there's an 5 over here. I'm sorry, I forgot that. Now this is 48. 40. No, this is 16. This is 16. Okay, so 48 root 5 by 16 root 5, which is 3. Is f of 3? 1, 1, 2, 3. Yes. See, this is correct. You can also check this in the calculator for all the bigger powers. This will work. I know that. I should not be missing over here. Yeah, you can check it yourself. So yeah, we have finally got the nth power of Fibonacci numbers using just some random logics. And yeah, so just some random manipulations, random things like eigenvectors, eigenvalues. We'll just use our intuition. We also observe new things, how we can exponentiate the matrix to any power. Yeah, I think this journey was fun, as I promised you in the beginning. I hope you really enjoyed this video. Right now, yeah. Also, I personally, when I did know this formula for a long time, but I never like really proved it this way. And when I realized a few days back that yes, I can actually do it this way, and it's so short, I was so impressed with this and with myself for finding such thing. Though it might have been already found by others, but still, I found it on my own, and I felt pride for that. And yeah, again, at that time, I immediately thought of making the video. And yeah, today after making this video, I feel like I have done justice to how good this content was. I feel that I have been able to deliberate well. Yeah, and I hope that you did enjoy. You learned something new. If yes, do share with your friends too. We have to raise 3,000 watch hours sooner so that I can monetize the channel and I can earn from it. Yeah. Okay, that's it. Thanks for watching and look forward to seeing you in the upcoming videos too.